Now that we have a redox table, how can we use it to predict any spontaneous redox reaction? Well, when we do this, we have to do a number of things. First thing we want to do is we want to list all of the entities present. We want to classify them as oxidizing agent and reducing agents. Identify the strongest oxidizing agent, strongest reducing agent, and then we'll predict whether the reaction is spontaneous. We'll write our half reactions. We'll use our multipliers to balance the electrons, and we'll combine. So let's take a look at a couple of examples. So the first question, will a spontaneous reaction occur if a lead strip is added to a silver nitrate solution? So first thing, I list all my entities. So I have lead, I have silver ion, I have nitrate ion, and because it's a solution, I also have water. Okay, so now I'm going to classify them as either oxidizing agents or reducing agents. Okay, so what we'll do is we'll look at our redox table, and we're going to look for each of the things on the table. And we're going to mark off where they are. So I've marked off my lead, my silver ion. We have nitrate, but it needs acidic protons, which we don't have. And we have water, and water appears twice in the table. So as a result, this allows me to label my oxidizing and reducing agents. We know solid lead would be a reducing agent because it can only undergo oxidation. My silver ion is an oxidizing agent because it can only undergo oxidation. Water can be both. Because I don't have any acidic protons, my nitrate ion will not be involved in any reactions. My next thing will be to identify the strongest oxidizing agent, strongest reducing agent. And because the silver is the highest on the left, that makes it my strongest oxidizing agent. And because my lead is the lowest on the right, that makes it my strongest reducing agent. Okay, now I'm going to predict whether a spontaneous redox reaction will occur. And as we know, if my strongest oxidizing agent is above my strongest reducing agent, a spontaneous redox reaction will occur. So in this case, this oxidizing agent is above this reducing agent, so I'll get a spontaneous redox reaction between them. Because this oxidizing agent is below this reducing agent, I will not get a spontaneous reaction between them. Likewise, this oxidizing agent is below this reducing agent, so I will not get a spontaneous reaction between them either. The oxidizing agent has to be above the reducing agent. Okay, so now I'm going to write my half reactions. I'm just going to copy them from the table. So I copied the silver reaction, and then I copied the lead, and because it's undergoing oxidation instead of reduction, and these are reduction half reactions, all I did was flip the reaction. Okay, then I'm going to determine my multiplier to balance the number of electrons lost and gained. So therefore I multiply my first reaction by 2, and then I'm going to combine them. This would be my spontaneous redox reaction if I put a lead strip in a silver nitrate. Let's take a look at a second example. Okay, so will a spontaneous reaction occur if a tin 2-bromide solution is poured into a acidified sodium dichromate solution? So first we identify all of our entities, so a tin 2 ion and a bromide ion for my first solution, a chromate ion and a dichromate ion and a sodium ion for my second solution, acidic proton because it's acidified, and water because they're both solutions. Then I'm going to go to my redox table and identify them. So I'm going to look for chromate, water, bromide, tin 2, proton, tin 2. So tin 2 can be both an oxidizing agent and reducing agent, just like water can be both an oxidizing agent and reducing agent. And sodium ion. Okay. So because when my chromate is an oxidizing agent, it requires an acidic proton. What I'll do is I'll show this joining to show that these two work together as an oxidizing agent. So my tin 2 ion can be both an oxidizing agent, reducing agent. My water is both an oxidizing agent, reducing agent. There are my other oxidizing agents. I have one other reducing agent. Then we're going to identify our strongest oxidizing agent and strongest reducing agent. So my highest on the left is my dichromate with acidic proton. and my lowest on the right is my tin 2. So therefore a spontaneous redox reaction will occur between them. Okay? But my strongest oxidizing agent is above this reducing agent, so I could get a spontaneous redox reaction occurring between them as well. Likewise, my strongest oxidizing agent is above this reducing agent, so I could also get a spontaneous redox reaction occurring there. So in this case, this combination would give me 3 different redox reactions because my strongest oxidizing agent is above 3 different reducing agents. So therefore, what I'm going to do is I'm going to write the half reactions for each of them now. So there's my half reaction for my strongest oxidizing agent. And I'm going to start with the reducing agent that's the furthest away because that's the reaction that's most likely to occur. And then I have my second furthest away, and finally my closest. And remember, because these are now oxidizing reactions, I write the reverse reaction. Okay, now I'm going to determine the multipliers to combine each of these reactions together. So if I multiply this one by 1 and 1 by 3, I'll have 6 electrons each. 1 and 3, 6 electrons each. And then 2 and 3 to give me 12 electrons. And then I'm going to apply my multiplier, and then I'm going to add my reactions, each of the pairs of reactions together. And so in this combination, I could get 3 potential spontaneous redox reactions. The one that is most likely to occur is the one where my oxidizing agent and reducing agent are the furthest from each other. The one that's least likely to occur is when they're the closest to each other.